Picture a world where the sky is never still, where twin suns whirl in an endless celestial dance, casting shifting shadows and painting the horizon with double sunrises and sunsets. This isn't science fiction, it's the reality of planets orbiting binary star systems, places where the rules of day and night as we know them don't apply. Imagine standing on the surface of such a world, feeling the heat of two stars instead of one, watching as their gravitational pull shapes the very fabric of existence around you. It's a spectacle that defies our earthly expectations, a reminder of just how diverse and strange the universe can be. But here's the real question: could life, alien life, find a way to thrive in such a chaotic and radiant environment? The idea of life flourishing under twin suns isn't just a fantasy, it's a scientific possibility that challenges everything we thought we knew about habitability. On Earth, life clings to the delicate balance of a single star's warmth, but out there in the vast cosmic tapestry, planets locked in the gravitational embrace of two stars might carve out their own paths to survival. Think about it: double the light, double the energy, but also double the challenges. How would ecosystems adapt to the relentless ebb and flow of stellar radiation? Could evolution engineer creatures capable of weathering the extreme tides, the blistering heat waves, or the eerie twilight of a world caught between two competing sources of light? This is the mystery we're about to unravel, a journey into the heart of one of astrophysics' most tantalizing questions. We'll explore the cutting-edge research that suggests binary star systems could be hotbeds for alien life, diving into the strange and wonderful adaptations that might evolve under double suns. From planets with skies perpetually ablaze to moons where shadows never settle, the possibilities are as endless as they are awe-inspiring. So buckle up, because by the time we're done, you'll never look at the night sky the same way again. Binary star systems where two stars orbit a common center of gravity are far more common in the universe than you might think. In fact, astronomers estimate that nearly half of all sun-like stars have a stellar companion, making these cosmic duos a standard feature of our galaxy rather than a rare oddity. But how do such systems form? Picture a colossal cloud of gas and dust collapsing under its own gravity, fragmenting as it spins until two distinct stars emerge, forever bound in an intricate gravitational waltz. Unlike our solitary solar system, where Earth basks in the steady glow of a single sun, planets in binary systems experience a celestial tug-of-war where light, heat, and even time itself are shaped by the competing pull of two brilliant stars. These stellar pairs come in two main flavors: close binaries, where stars orbit so tightly they could fit within our solar system, and wide binaries, separated by distances that could swallow entire planetary systems. Take Alpha Centauri, the closest star system to Earth, a wide binary where two sun-like stars dance roughly as far apart as Saturn is from our Sun. Then there's the more extreme cases, like the eclipsing binary Algol, nicknamed the Demon Star, where two stars circle so close they regularly steal material from one another, creating dazzling but violent displays of cosmic cannibalism. The very existence of these systems shatters our earthly assumptions about stability. For a planet orbiting a binary pair, the rhythm of day and night isn't just unpredictable, it's a spectacle. Some worlds might experience perpetual daylight as their twin suns take turns bathing them in light, while others could endure wild temperature swings as gravitational forces stretch and squeeze their orbits. Yet against all odds, recent simulations suggest that habitable zones, regions where liquid water could persist, do exist in these chaotic environments. The key lies in the stars' dance. If they orbit each other at just the right distance, their combined gravity carves out a stable pocket where life, against the cosmic odds, might just find a way. The gravitational ballet between two stars in a binary system is a spectacle of cosmic forces, where every movement sends ripples through the fabric of space and time. Unlike our Sun's lonely dominion, binary stars exist in a perpetual push and pull, their orbits locked in a delicate balance of attraction and momentum. Some circle each other in tidy, near-perfect rings, while others trace wild, elongated paths that bring them perilously close before flinging them apart again. This dance isn't just for show. It shapes everything from the birth of planets to the very conditions that might make life possible. Take tidal forces, for example. Just as the moon tugs at Earth's oceans, the gravitational pull between binary stars can stretch and distort their shapes, heating their interiors through friction and sometimes even stripping away layers of stellar material. In tight binaries, this can lead to dramatic exchanges of gas and energy, creating swirling disks of debris where planets might one day form. But here's the twist: these same forces can also tear nascent worlds apart before they've had a chance to solidify. For a planet to survive in such a chaotic nursery, it needs to find a sweet spot, a stable orbit where the competing pulls of the two stars cancel each other out, a celestial tightrope walk few worlds manage to achieve. Then there's the habitable zone, that Goldilocks region where temperatures are just right for liquid water. Around a single star, it's a relatively straightforward band, but in a binary system, things get complicated. The zone isn't static. It wobbles and shifts as the stars move, sometimes overlapping, sometimes splitting into separate pockets. A planet might bask in warmth for decades, only to be plunged into icy darkness as its suns swing apart. Yet some simulations suggest these very fluctuations could drive evolution in unexpected ways, fostering life forms that adapt to extremes, thriving in brief windows of opportunity between stellar seasons. The most surprising part: binary systems might actually enhance the chances for life in ways we're only beginning to understand. Twin stars can extend a planet's habitable lifespan, offering backup heat when one star fades, or their combined light could power photosynthesis for organisms tuned to a broader spectrum. Imagine forests that glow under the mixed hues of two suns, or tides shaped by competing gravitational rhythms. It's a reminder that life, if it's out there, won't play by Earth's rules, it'll rewrite them entirely. Building a planet is no easy feat even under ideal conditions. But throw in a second star, and the process becomes a cosmic obstacle course where gravity, chaos, and sheer chance dictate survival. In binary star systems, the delicate ballet of planetary formation faces hurdles we can scarcely imagine. Picture a swirling protoplanetary disk, the birthplace of planets stretched and warped by the competing pull of two stars. Instead of a neat, flat ring of dust and gas, these disks often become lopsided, fractured, or even torn apart entirely. Some are funneled into bizarre spiral shapes, while others are stripped of their material before planets can coalesce. It's like trying to bake a cake in a hurricane. The ingredients are there, but the environment refuses to cooperate. Yet against these odds, planets do form in binary systems. Take Kepler-34b, a gas giant orbiting twin suns nearly 5,000 light-years away. This world shouldn't exist according to early models. Its birthplace was a maelstrom of gravitational forces. So how did it emerge intact? The answer lies in resilience and adaptability. Some protoplanetary disks orbit just one of the two stars, staying far enough from their companion to avoid disruption. Others find stability in wide, circumbinary orbits, threading the needle between the star's gravitational influence. These Tatooine-like worlds, named after Luke Skywalker's fictional home, carve out paths where the competing tugs of their suns cancel out, creating pockets of calm in the storm. But even then, the challenges don't end. Planets forming in binary systems face relentless gravitational harassment. Their orbits can be stretched, tilted, or even ejected entirely if the star's dance grows too erratic. Smaller rocky worlds like Earth are especially vulnerable. They need time to accumulate material, but binary stars often fling that material away before it can clump together. Yet nature finds a way. Some theories suggest that planets in these systems might form faster, condensing in a rush before chaos takes hold. Others propose that binary stars could actually help by stirring up the disk, triggering collisions that accelerate planet growth. It's a cosmic paradox. The same forces that threaten to destroy these worlds might also be the key to their creation. The magic lies in balance. Too close to the stars and a budding planet is ripped apart. Too far and it's frozen in the outskirts, but in that narrow band of possibility where heat, gravity, and timing align, a world can emerge defying the odds. And if it does, the rewards could be extraordinary. Planets forged in such turbulence might develop denser cores, stronger magnetic fields, or even exotic chemistries unlike anything in our solar system. They're survivors shaped by fire and chaos, and that could make them the ultimate cradles for life, if they can endure the dance of their twin suns. In our solar system, the habitable zone is a straightforward concept, a neat band around the sun where temperatures allow liquid water to exist. But toss a second star into the mix and suddenly, just right becomes a cosmic moving target. Binary star systems turn the Goldilocks zone into a dynamic, shape-shifting phenomenon where stability is fleeting and adaptability is key. Picture this: two stars, each with their own habitable zone, orbiting one another. As they move, their zones overlap, separate, and sometimes even merge, creating pockets of opportunity that flicker in and out of existence like celestial strobe lights. A planet might spend part of its orbit bathed in warmth from both suns, only to later find itself stranded in the cold as the stars pull apart. This isn't just theoretical. We've already spotted real-world examples. Take Kepler-47, the first known circumbinary system with planets orbiting both stars. Here, the habitable zone isn't a static ring but a donut-shaped region that wobbles as the stars dance. One of its planets, Kepler-47c, skirts the outer edge of this zone, enduring wild temperature swings that would make Earth seasons seem tame. Yet, if it has a thick atmosphere or deep oceans, it might just redistribute that heat, creating niche environments where life could cling on. The real puzzle lies in the timing. For life to emerge, a planet needs consistency, enough time for chemistry to become biology. But in binary systems, the window of habitability can slam shut unpredictably. A world might enjoy millions of years of temperate bliss before its stars' shifting orbits plunge it into a deep freeze or scorch it dry. Yet nature has a knack for exploiting chaos. Some organisms on Earth thrive in places we once thought uninhabitable: geothermal vents, acidic lakes, even the vacuum of space. Could life in binary systems evolve to hibernate during cold spells or photosynthesize under the mixed light of two stars? The overlap of their habitable zones might create hybrid environments where the combined energy fuels life in ways we've never seen. Here's where it gets even stranger. Binary stars aren't always identical. Imagine a fiery blue star paired with a cooler red dwarf. Their habitable zones don't just shift, they warp. The hotter star's zone stretches far out while the dimmer one's hugs close. A planet orbiting both could experience alternating waves of intense radiation and gentle warmth, pushing evolution to craft creatures with built-in sunscreen or reflective skins. Or consider tidally locked worlds where one side always faces the stars and the other lingers in darkness. With two suns, the Terminator line, the twilight border between day and night could become a fertile strip bathed in perpetual golden hour. The takeaway: binary systems don't just complicate the habitable zone, they reinvent it. What seems like a disadvantage might actually be a catalyst for life we can't yet imagine. If Earth teaches us anything, it's that life thrives on the edge of possibility, and in the kaleidoscopic skies of twin suns, the edge is everywhere. Imagine living on a planet where the horizon is dominated not by one, but two suns, each rising and setting in a celestial rhythm so complex, you'd need an astronomer's intuition just to predict the next sunrise. This isn't just the stuff of Star Wars Tatooine. It's the reality of circumbinary planets, worlds that orbit both stars in a binary system, locked in a gravitational embrace with two fiery masters. The most famous real-world example, Kepler-16b, a gas giant dubbed the original Tatooine after its discovery in 2011. Here, the sky is a theater of constant motion, where the stars pirouette around each other every 41 days, casting ever-shifting patterns of light and shadow across the planet's atmosphere. Days on Kepler-16b defy earthly logic. Instead of a steady arc across the sky, its twin suns, one smaller and orange, the other larger and yellow, dance in and out of alignment, creating sunrises and sunsets that vary wildly in brightness and color. Sometimes both stars rise together, flooding the landscape with a surreal, blended glow. Other times, one lingers low on the horizon while the other climbs high, stretching shadows into bizarre, elongated shapes. And when the stars eclipse each other, as they do regularly, the planet plunges into a sudden, eerie twilight, a reminder of the delicate balance that governs its existence. But the real marvel lies in the sunlight itself. With two stars contributing energy, the light spectrum on a circumbinary planet isn't just doubled, it's transformed. The cooler star bathes the world in reddish hues, while its hotter companion bleeds through with aggressive blue-white rays. For any potential life forms, this could mean evolutionary adaptations unlike anything on Earth. Picture plants with leaves tuned to absorb multiple light frequencies, or creatures whose vision spans a broader range of colors to navigate the shifting tones of their double-starved sky. What's even more fascinating is how these planets manage to exist at all. Orbiting two stars requires threading a gravitational needle too close, and the competing pulls would rip a world apart too far, and it'd be flung into the void. Kepler-16b orbits at a cautious distance, far enough to avoid chaos but close enough to feel the star's combined warmth. It's a testament to the universe's ingenuity. Even in the most turbulent environments, nature finds a way to carve out pockets of stability. And if a gas giant can survive here, who's to say a rocky, Earth-like world couldn't do the same, perhaps with its own secrets hidden beneath those twin suns? Some worlds don't just have two suns, they're trapped in an endless day where the concept of night vanishes entirely. Picture a planet so tightly bound to its stars that one side always faces them, locked in a gravitational embrace that never lets the sky grow dark. This isn't just a quirk of orbit, it's a total reimagining of what a habitable world could look like. On Earth, our rhythmic cycle of day and night shapes everything from weather to ecosystems, but on a tidally locked planet circling twin suns, the rules change dramatically. The climate here would defy earthly logic. One hemisphere, forever scorched by the relentless glare of two stars, would become a blistering desert where water evaporates faster than it can condense. Meanwhile, the far side, shrouded in permanent darkness, might plunge into an icy wasteland where atmosphere freezes solid. But between these extremes lies a narrow band of twilight, a ring of twilight where temperatures could hover in a life-friendly range. Here, the sky might glow with a perpetual golden hue as the stars hover just above the horizon, neither rising nor setting, casting long shadows that never move. Weather patterns would be equally surreal. Without the cooling respite of night, heat builds endlessly on the dayside, driving hurricane-force winds as the atmosphere struggles to redistribute energy. Storms could rage along the twilight belt, fueled by the violent clash of hot and cold air. Imagine endless thunderstorms, their lightning illuminating a landscape where plants, if they exist, might lie flat to avoid desiccation or grow translucent to filter the excess light. Life here would need radical adaptations. Organisms might evolve internal clocks tuned not to light cycles but to atmospheric changes like pressure drops signaling an approaching superstorm. Photosynthetic life could cluster in the twilight zone, their leaves blackened to absorb every scrap of energy from the dim, double sunlight, and predators. They might rely on heat sensing or seismic vibrations to hunt in a world where visual cues are static. But the most fascinating possibility isn't just survival, it's innovation. On a planet where resources are concentrated in that fragile twilight strip, life could evolve unheard of strategies to endure. Hardy lichens might spread like carpets, anchoring themselves against eternal winds. Creatures could develop mirrored skin to reflect excess heat or bioluminescence to navigate the dark side's frozen caves. For civilizations, the challenges multiply. Agriculture would demand precision engineering, perhaps hydroponic towers rotating to balance light exposure, while architecture might prioritize thermal regulation over aesthetics. Yet the rewards could be profound. A world where solar energy is inexhaustible, where the sky itself is a constant reminder of nature's boundless creativity. In the unending daylight of twin suns, life wouldn't just adapt, it would reinvent itself. Surviving on a planet with two suns means weathering temperature swings that would make Earth's most extreme climate seem mild. In binary star systems, a world's fate hinges on the stars' dance, whether they whirl tightly together or stretch apart in elongated orbits. When the stars eclipse each other, their combined light can vanish in minutes, plunging the planet into a sudden, bone-chilling freeze. Then, as they swing back into alignment, the return of double sunlight might scorch the landscape like a celestial magnifying glass. These aren't gradual seasonal changes, they're violent, rapid shifts that reshape entire ecosystems in the span of days. Take a planet like Kepler 35b, where each year lasts just 131 Earth days. As its two suns, one slightly smaller than ours, the other a dimmer orange dwarf, orbit each other, the planet's surface temperatures can swing by hundreds of degrees. During a close stellar approach, the twin suns might blast the world with relentless infrared and ultraviolet radiation, boiling away surface water. But when they drift apart, the weakened light could trigger a flash freeze, encasing lakes in ice almost overnight. Life here would need survival strategies ripped from science fiction. Some organisms might evolve antifreeze proteins, like those in Arctic fish, to prevent cell rupture during sudden cold snaps. Others could develop reflective outer layers to deflect excess heat, or burrow deep underground where temperature shifts are less extreme. Photosynthetic life wouldn't rely on steady sunlight. It might harvest energy in furious bursts during peak stellar alignment, then hibernate in spore-like states when darkness returns. Perhaps the most ingenious adaptation would be migration. Imagine vast herds of creatures or even entire forests of mobile, rootless plants slowly shifting across the landscape with the star's rhythm, following the narrow band where temperatures remain tolerable. Or consider microbial mats that rise and retreat with the heat, blooming across deserts when the suns are close, then retreating into subterranean vaults when the cold descends. Civilizations, if they exist, would face even starker challenges. Architecture couldn't be static. Buildings might need retractable insulation or rotating panels to regulate heat absorption. Agriculture would demand hydroponic towers with adjustable light filtering, or underground fungal farms fed by geothermal warmth. And timekeeping. Forget calendars based on seasons. Societies might track stellar positions down to the hour, with entire cultures organized around predicting the next temperature spike or plunge. Yet within this chaos lies an unexpected advantage. Extreme fluctuations can drive rapid evolution, forcing life to innovate or perish. On Earth, the most resilient organisms often emerge from the harshest environments: deep-sea vents, acid pools, frozen tundras. In a binary system where change is the only constant, life might evolve unmatched versatility, thriving not despite the chaos but because of it. The very forces that seem hostile could be the crucible for something extraordinary, a biosphere unlike any we've ever imagined. The gravitational pull of twin suns doesn't just shape orbits, it can twist a planet's very core into turmoil. When two stars exert their combined tidal forces, they don't merely create gentle waves, they sculpt entire landscapes through sheer celestial friction. Imagine a world caught in this cosmic tug-of-war, where the ground itself flexes and groans under the strain. Like kneading dough, these relentless tugs generate internal heat through friction, a process called tidal heating, turning the planet's mantle into a simmering cauldron of molten rock. Jupiter's moon Io offers a sneak preview of this chaos. Bathed in the gas giant's gravitational embrace, it's the most volcanically active place in our solar system, spewing lava fountains miles high. Now amplify that by 2 stars instead of 1, and you've got a recipe for planetary pandemonium. Some binary systems crank this effect to extremes. Take a close-orbiting planet circling 2 tightly knit stars. Every rotation stretches its crust thinner, triggering volcanic eruptions that could last millennia. Rivers of magma might carve continents in real time, while superheated geysers blast atmospheric gases into space. But the real danger isn't just the eruptions, it's the slow suffocation. A planet's atmosphere, pummeled by stellar winds from 2 directions, could erode like sand in a hurricane. Venus, despite its thick cloak of carbon dioxide, shows how solar winds can strip away lighter elements over time. Now picture that assault doubled, with atmospheric particles torn away by competing gravitational tides before they even reach the upper atmosphere. Yet here's the paradox: this very violence might forge unexpected havens. Tidal heating could maintain subsurface oceans on frozen worlds, much like Saturn's icy moon Enceladus, where geothermal warmth keeps water liquid beneath miles of ice. A binary system's gravitational kneading might prevent these hidden seas from freezing solid, offering refuge for extremophile life. Or consider atmospheres. While some planets lose theirs entirely, others might replenish them through constant volcanic outgassing, creating a precarious equilibrium where skies reform as fast as they're stripped away. The ultimate wildcard: magnetic fields. A planet with a robust magnetic shield generated by a churning molten core could deflect stellar winds better than Earth does. But in binary systems, tidal forces might distort or even shut down that protective dynamo altogether, leaving the surface exposed. Alternatively, the added heat could supercharge the core, producing a magnetic field so strong it creates auroras visible from space. For potential life, these extremes rewrite the rulebook. Microbes might thrive in scalding volcanic vents, their biochemistry tuned to harness geothermal energy rather than sunlight. More complex organisms could evolve rapid life cycles to repopulate after catastrophic eruptions, or develop radiation-resistant traits to survive under thinned atmospheres. Entire ecosystems might cling to transient oases, volcanic hotspots that shift as the planet's crust buckles under changing tidal pressures. What emerges is a dizzying realization: in binary systems, habitability isn't about stability. It's about resilience, the ability to endure chaos and repurpose it. The same forces that sterilize one world might ignite the spark of life on another. And if life does take hold here, it won't just survive the storm, it'll harness it. Radiation in a single star system like ours is already a formidable force. Our sun bombards Earth with ultraviolet light, solar flares, and cosmic rays that would be lethal without our atmosphere and magnetic shield. But in a binary star system, the radiation environment cranks up to 11, creating a gauntlet of high-energy particles and electromagnetic fury that could sterilize a world or push life to evolve unprecedented defenses. The first danger comes from stellar flares. While our sun occasionally unleashes bursts of charged particles, binary stars, especially close pairs, can trigger synchronized flare events where one star's eruption destabilizes its companion, leading to back-to-back storms. Picture a planet caught in the crossfire. Just as it recovers from one star's flare, the second star delivers a knockout punch, stripping away atmospheric layers and dousing the surface in X-rays. Red dwarfs, the most common stars in binary systems, are notorious for such violence. Their flares can outshine the star itself for minutes, bathing nearby planets in enough UV radiation to shred DNA. But flares are just the beginning. Binary systems often generate higher baseline UV levels due to their combined stellar output. Earth's ozone layer blocks most ultraviolet light, but a planet orbiting two stars might need double the protection or face permanent mutations in its surface life. Some microbes on Earth, like the radiation-resistant Deinococcus radiodurans, can repair shattered DNA after extreme UV exposure. Could similar organisms evolve under twin suns, developing biological, sunscreen pigments or UV-reflecting exoskeletons? Then there's cosmic rays, high-energy particles from deep space that binary stars can amplify. When two stars orbit closely, their overlapping magnetic fields create chaotic zones where cosmic rays get trapped and accelerated like stones in a slingshot. Without a robust magnetic field, a planet might suffer constant particle bombardment, sterilizing its surface. But life could retreat underground or underwater, as it did on early Earth during solar storms. Hydrothermal vents shielded by miles of ocean might become bustling metropolises for extremophiles thriving in the dark, the ultimate wildcard, stellar evolution. Unlike solitary stars, binaries can transfer mass between each other as they age, altering their radiation profiles unpredictably. A once mild star might suddenly flare up after siphoning material from its partner, turning a habitable world into a wasteland. Yet here's the twist. Some studies suggest binary stars might protect planets by sharing the radiation burden. If one star's outbursts are absorbed by its companion's magnetic field, the combined system could counterintuitively offer a more stable environment over time. Survival here demands creativity. Life might cloak itself under thick ice sheets like Europa's hidden ocean, or evolve rapid cellular repair mechanisms to weather daily radiation storms. Photosynthetic organisms could switch to chemosynthesis during flare events, while others develop metallic compounds in their tissues to deflect ionizing particles. And if intelligence emerges, civilizations might build their cities in caves or beneath reflective domes, treating their twin suns not as nurturers but as capricious gods to be appeased. The lesson is clear. Binary systems don't just intensify radiation, they redefine what adaptation means. Where one world perishes, another might forge life forms tougher than anything Earth has ever seen, turning a cosmic death zone into a crucible for resilience. Moons have always been the quiet underdogs of habitability, often overshadowed by their parent planets, yet hiding secrets that could rewrite the rules of where life thrives. In the chaos of binary star systems, where planets endure scorching heat waves, gravitational whiplash, and relentless radiation, there's another possibility: gas giant moons. These unassuming worlds tethered to massive planets might just be the ultimate sanctuaries, places where stability emerges from the surrounding cosmic storm. Think of them as nature's bunkers, shielded not just by distance but by the sheer bulk of their planetary guardians. Take tidal forces, for instance. A moon orbiting a gas giant experiences constant gravitational kneading from its host planet, generating internal heat through friction. This isn't just a side effect, it's a built-in furnace. Europa, one of Jupiter's moons, likely harbors a subsurface ocean kept liquid by this very process, despite being far from the sun's warmth. Now imagine a similar moon in a binary system, where twin stars bombard it with erratic energy. The gas giant's gravity could counteract the stellar chaos, creating a thermal equilibrium that prevents deadly temperature swings. While the planet itself might be a turbulent hellscape, its moons could enjoy a surprisingly temperate climate, their oceans shielded beneath miles of ice. Then there's radiation. Gas giants are cosmic shields, their magnetic fields deflecting stellar winds that would otherwise scour a moon's atmosphere. Earth's magnetosphere protects us from the sun's worst outbursts, but a moon nestled within a gas giant's magnetic embrace gets double the defense, especially in a binary system where radiation comes from two directions. Even if the stars unleash synchronized flares, the parent planet's magnetic umbrella might absorb the worst of the barrage, leaving the Moon's surface relatively unscathed. Life here wouldn't need to evolve extreme radiation resistance. It could thrive in the quiet lee of its colossal neighbor, but the real magic lies in orbital dynamics. Moons in binary systems don't just orbit their planets, they exist within a layered gravitational ballet. A gas giant's pull can stabilize a moon's orbit, preventing the wild swings that plague standalone planets. While a lone world might be ejected or torn apart by the stars' competing tugs, a moon stays securely anchored, its path smoothed by the planet's dominance. This stability buys time for atmospheres to develop, for chemistry to simmer, for life to gain a foothold. Picture a moon like Kepler 1625b, a hypothetical exomoon candidate discovered by astronomers. Bathed in the reflected glow of its gas giant and the distant light of twin suns, its skies could be a canvas of surreal beauty. The primary star might dominate the day, while the secondary star paints the horizon at dusk, their combined gravitational nudges keeping the moon's tides in a delicate rhythm. Subsurface oceans, warmed by tidal forces and shielded by ice, could teem with life utterly alien to Earth, organisms tuned to the faint vibrations of their planetary host, or photosynthetic microbes harvesting the blended light of two suns filtering through icy crevices. The irony is poetic. In systems where planets face relentless upheaval, moons might be the true oases. They're the Goldilocks zones within Goldilocks zones, worlds where protection, warmth, and stability converge not by stellar benevolence, but by the silent, steadfast pull of a gas giant. If life exists in binary systems, it might not be on the planets we've imagined. It could be hiding in plain sight, clinging to the skirts of giants. Plants on Earth have perfected the art of harvesting sunlight over billions of years, tuning their leaves to the steady rhythm of a single star. But drop them onto a planet with two suns and their playbook gets tossed out the airlock. In a binary star system, photosynthesis wouldn't just adapt, it would reinvent itself, driven by the chaotic ballet of dual light sources competing for dominance. Picture a world where plant-like organisms face a relentless flood of energy, their leaves bombarded by overlapping spectra from stars of different colors and intensities. Some might develop mirrored surfaces to reflect excess radiation, while others could evolve dual pigment systems like a painter mixing colors from two separate palettes to capture every drop of usable light. The challenges go beyond mere intensity. Earth's plants rely on predictable day-night cycles to regulate photosynthesis, but under twin suns, daylight could last for weeks or vanish in hours. Organisms might evolve internal clocks that track stellar positions rather than time, triggering metabolic bursts when both stars align overhead. Others could become opportunists, storing energy in dense, tuber-like structures during periods of constant light, then metabolizing reserves during eclipses or extended darkness. Imagine forests where some plants unfurl only when the red sun dominates, while others thrive under the blue star's harsher glare, a botanical division of labor carved by spectrum and survival. Then there's the question of efficiency. Earth's chlorophyll absorbs mostly red and blue light, leaving green wavelengths to bounce back to our eyes. But under a binary pair where one star might emit more infrared and the other ultraviolet, pigments could branch into entirely new chemical configurations. Some might develop layered leaves, with upper surfaces tuned to the hotter star's high energy light and lower layers specialized for the cooler star's glow. Others could evolve dynamic pigments that shift molecular structure based on which star is dominant, like living solar panels that recalibrate in real time. But the real game changer: shared energy networks. On Earth, plants compete fiercely for sunlight, but in a dual star environment, cooperation might prove more effective. Vines could link root systems to redistribute nutrients between shade dwellers and sun seekers, creating symbiotic superorganisms. Or consider towering, light scraper plants with vertically stacked leaves, each layer optimized for a different star's angle, nature's answer to multi-story greenhouses. The most radical possibility, photosynthesis without permanence. On a world where stellar alignments shift unpredictably, some organisms might abandon roots altogether, becoming mobile harvesters that crawl toward optimal light conditions. Picture a field of rolling, tumbleweed-like plants that reposition themselves as the stars move, or algae blooms that drift on tidal currents to chase the brightest patches of water. What emerges is a revelation. Binary stars don't just change how plants collect light, they redefine what a plant even is. Where Earth's flora evolved for stability, life under twin suns would prize flexibility above all else, crafting biology that bends to the whim of the heavens. And if we ever find such a world, its greenery might not look green at all, but a shimmering, ever-shifting tapestry of colors we've yet to name. While photosynthesis dominates life on Earth, twin sun planets might rewrite the rules entirely, because where sunlight is erratic or lethal, survival demands alternative energy sources. Imagine organisms that bypass starlight altogether, tapping into the planet's own restless energy. Around hydrothermal vents in Earth's deepest oceans, entire ecosystems thrive without sunlight, fueled by chemosynthesis, a process where microbes convert chemicals like hydrogen sulfide into energy. Now transplant that to a binary system's shadowed moon or a tidally heated world where volcanic fissures belch nutrients into icy seas. Here, life wouldn't just endure the darkness, it'd flourish, with chemosynthetic bacteria forming the base of a food web that supports towering tube worms, armored crustaceans, and predatory species adapted to the perpetual night. But chemosynthesis is just the beginning. Binary systems churn with gravitational friction, and that energy doesn't vanish, it ripples through planets as tidal force. On a world with two suns, oceans could slosh violently between stellar pools, generating currents strong enough to power entire ecosystems. Picture kelp-like organisms anchored to the seabed, their fronds covered in microscopic turbines that harness kinetic energy from the water's motion, or colonies of filter feeders that pulse in sync with tidal rhythms, extracting nutrients stirred up by the chaos above. Even on dry land, the planet's flexing crust might release geothermal heat through cracks, creating oases like hot springs where heat-loving microbes convert rock minerals into sustenance. Then there's atmospheric harvesting. Binary stars often blast planets with charged particles, but some extremophiles on Earth, like the bacterium Candidatus desulforudis audax viator, survive by metabolizing radioactive decay. On a high radiation world, organisms might evolve to directly absorb and process stellar wind particles, turning a lethal environment into a buffet. Their cells could contain miniature lightning rods to capture atmospheric electricity during solar storms, or pigments that convert cosmic rays into usable energy, glowing faintly in the perpetual twilight. The real wildcard, hybrid life forms. In a system where energy sources fluctuate wildly, some organisms might switch metabolic strategies like flipping a switch. Algae-like creatures could photosynthesize during brief calm periods, then retreat into chemosynthetic hibernation when flares erupt. Others might form symbiotic partnerships. Imagine a mobile predator that carries chemosynthetic bacteria in specialized organs, farming them for energy during eclipses when its usual prey vanishes. Civilizations, too, would adapt ingeniously. A species evolving in such a world might skip fossil fuels entirely, building their infrastructure around tidal generators or geothermal taps. Their cities could cluster near volcanic rifts, where the planet's inner heat provides both warmth and power, or float on oceans crisscrossed with energy-harvesting membranes. The lesson is stark yet inspiring. Life under twin suns wouldn't just cling to Earth's playbook. It'd draft a new one where energy isn't a single thread of sunlight, but a tangled web of opportunity, pulled from the planet's bones, the star's fury, and the void between. And in that struggle, it might uncover possibilities we've yet to dream of. The Drake equation, that famous formula for estimating the number of detectable civilizations in our galaxy, has always been a thought experiment built around stars like our own. But what happens when we plug binary systems into the equation? Suddenly, every variable gets a cosmic asterisk, challenging our assumptions about where and how life might arise. Let's break it down factor by factor, starting with star formation. Binary systems aren't just common, they're nearly half the stellar population in the Milky Way. That means the first term in the equation, the rate of star formation suitable for life, effectively doubles when we account for twin suns. But here's the catch: not all binaries are created equal. Tightly orbiting pairs might shred protoplanetary disks before worlds can form, while wider binaries could offer stable nurseries. The math isn't just about quantity, it's about orbital dynamics. Next, consider the fraction of stars with planets. Kepler's discoveries proved planets can survive in binary systems, but their architectures defy our solar system's tidy blueprint. Circumbinary planets, those orbiting both stars, tend to be gas giants, while single-star planets in binaries face erratic climates. Does this skew the odds? Perhaps Earth-like worlds might be rarer in binaries, but if they exist, their environments could turbocharge evolution. Imagine a planet where tidal forces and radiation pressure accelerate genetic diversity, shortening the leap from microbes to intelligence. On the other hand, extreme conditions might prune life back to extremophiles, stalling complexity. The equation's terms for habitable planets and life's emergence aren't just numbers here, they're roller coasters. Then there's the fraction of life that becomes intelligent. Binary systems could be crucibles for intelligence or cosmic dead ends. Constant environmental upheaval might favor generalists over specialists, pushing life toward adaptability rather than tool use. Or conversely, the need to predict eclipses, stellar flares, and climate swings could select for problem-solving skills, accelerating cognitive leaps. Picture a civilization that charts its history not in seasons but in stellar alignments, its science born from the need to survive celestial chaos. Finally, the lifespan of civilizations. Binary stars complicate this variable most of all. Close pairs can undergo catastrophic mass transfers, while wider binaries might offer stability for billions of years. A civilization rising in such a system wouldn't just contend with its own hubris, it'd face the looming threat of stellar evolution. But there's a twist. Twin stars might buy civilizations extra time. As one star ages out of the habitable zone, its companion could pick up the slack, extending the window for technological growth. The verdict: binaries don't simplify the Drake equation, they explode it into a fractal of possibilities. For every factor that seems to hinder life, another might amplify it. The universe loves balance. Where chaos reigns, resilience follows. And if we ever detect a signal from a binary system, it won't just answer the equation, it'll rewrite it. Building a civilization is hard enough on a stable planet, but try doing it on a world where the ground shakes from tidal forces, the sky flickers between two suns, and asteroid impacts rain down like clockwork. For intelligent life in a binary star system, survival isn't just about ingenuity, it's about rewriting the very definition of stability. Consider the asteroid threat alone. Our solar system's asteroid belt is a relatively placid neighborhood, but in a binary system, the gravitational tug of war between two stars can fling rogue rocks into chaotic orbits. A planet like Kepler 16b, nestled between its twin suns, might face bombardment rates 100 times higher than Earth's, with impacts large enough to reset evolutionary progress every few million years. Could any society advance past the Stone Age under such siege? Yet Earth's own history offers a paradoxical clue. The asteroid that wiped out the dinosaurs also cleared the stage for mammals to rise. In binary systems, frequent impacts could act as a brutal filter, crushing fledgling civilizations while accelerating adaptation in survivors. Imagine a species that evolves not just to endure disasters, but to anticipate them. Their astronomy might leapfrog ours by necessity, developing precise celestial mechanics to predict impact trajectories centuries in advance. Cities could be built underground or with self-sealing structures, while agriculture relies on radiation-hardened crops. Technology here wouldn't follow our linear path. It might jump straight to planetary defense systems, with early civilizations diverting asteroids before mastering electricity. Climate chaos poses an even thornier challenge. Earth's ice ages unfolded over millennia, allowing species time to adapt or migrate. But on a binary orbiting world, temperature swings could hit within generations or faster. A society might flourish during a warm interlude, building sprawling cities, only to see them buried under glaciers as the star's orbits shift. Yet again, extremophiles on Earth hint at possibilities. Bacteria like Deinococcus radiodurans survive freezing and thawing by repairing shattered DNA. An intelligent species might engineer similar resilience, perhaps hibernating through cold cycles or developing nanotechnology to rebuild infrastructure after each climate crash. The wild card is energy. Our industrial revolution relied on steady fossil fuel deposits, but a planet racked by tidal heating and stellar flares might lack stable coal beds or oil reserves. Instead, civilizations could leapfrog to geothermal or fusion power, harnessing the very forces that threaten them. Picture a culture that taps volcanic vents for electricity or cultivates bioengineered microbes to convert solar flares into stored energy. Their tech tree wouldn't mirror ours, it'd branch in radical directions, with societal continuity maintained through decentralized, disaster-proof grids. And then there's time. On Earth, we've had uninterrupted mostly progress for 10,000 years. A blink in cosmic terms. Binary star societies might rise and fall like waves, their knowledge preserved in indestructible crystal archives or encoded in self-repairing organic networks. Each collapse wouldn't reset to zero. It'd leave fragments for the next cycle to build upon. The result, a civilization that advances in fits and starts, its history not a straight line but a spiral ascending through the chaos. The ultimate twist, these very adversities could forge societies far more robust than our own. A species that weathers extinction-level events as routine might develop cooperative structures we can't fathom, with cultures prioritizing collective survival over short-term gain. Their art, science, and philosophy would be steeped in impermanence, creating not just survival strategies but transcendent ways of being. After all, humanity's greatest innovations often emerge from crisis. In a universe where binary stars are the rule rather than the exception, the most enduring civilizations may be those forged in the fire of perpetual tumult. Every signal we've ever sent into space, every radio transmission, laser pulse, or coded message assumes one thing: a quiet, predictable stellar neighborhood. But what happens when your sky is a roaring concert of two stars? For civilizations in binary systems, communication wouldn't just be about breaking through the void, it'd be about cutting through a storm. Imagine trying to whisper across a hurricane. That's the challenge intelligent life might face under twin suns, where stellar flares, gravitational interference, and overlapping radiation belts could drown out even the most powerful transmissions. The first hurdle is noise. Binary stars, especially close pairs, generate electromagnetic chaos. Their tangled magnetic fields accelerate particles to extreme energies, creating static that could scramble traditional radio signals like a blender. Earth's SETI program listens for narrowband signals, precise, artificial tones standing out against cosmic background noise. But in a binary system, those clean frequencies might be useless, buried under stellar static. Aliens here could develop entirely different strategies, perhaps encoding messages in pulsed X-rays that punch through the interference, or modulating data onto the star's own flare patterns, like hiding a message in a thunderstorm. Then there's timing. Our deep space communication relies on precise orbital mechanics, calculating when a signal will arrive based on Earth's predictable path around the Sun. But a planet circling two stars moves in loops within loops, its position a calculus nightmare. Local astronomers might invent new branches of math just to model their world's dance, leading to coordinate systems that look like abstract art to us. Picture a civilization where north isn't fixed but defined by the star's ever-shifting barycenter, or where calendars track not just planetary orbits but intricate resonance cycles between the suns. Their version of a GPS could involve real-time stellar alignment updates broadcast to every device, but the real mind-bender signal endurance. In our solar system, a message aimed at Proxima Centauri takes 4 years to arrive. In a binary system where stellar motions can warp space-time unpredictably, signals might distort mid-flight, requiring error correction algorithms we've yet to dream up. Aliens might encode data in quantum-entangled particles to bypass the noise, or deploy relay stations at gravitational sweet spots where signals amplify rather than scatter. Their entire concept of a network could revolve around exploiting chaotic dynamics using stellar winds as carrier waves, or piggybacking data onto the star's own magnetic pulses. The most profound difference might not be technical but philosophical. Our astronomy grew from tracking one sun's steady path. Theirs would be a science of probabilities where predictability itself is fluid. After generations of observing eclipses that never repeat exactly, their mathematics might favor fuzzy logic over our rigid equations, their telescopes programmed to hunt for patterns in apparent randomness. Even their concept of silence could differ. Where we hear static, they might discern meaning, trained by evolution to pass order from the symphony of two stars. If we ever intercept a signal from such a world, decoding it won't just require advanced tech, it'll demand a paradigm shift. Their message might not be a deliberate hello, but an accidental side effect of technologies built to navigate a universe far noisier than ours. And that's the thrilling thought. The cosmos doesn't just host life, it hosts ways of thinking, entire frameworks of knowledge shaped by skies we've yet to imagine. Tatooine's twin suns have become iconic, an image so ingrained in pop culture that it's hard to picture binary star systems any other way. But while Star Wars nailed the visual poetry of a double sunset, real binary systems are far stranger than Hollywood's dreamscapes. For starters, Luke Skywalker's home planet orbits its suns at a distance that would be catastrophic in reality. Kepler-16b, the real-life Tatooine, is a gas giant with a toxic atmosphere, not a desert world where you can casually sip blue milk. And those picturesque sunsets, on most binary planets, the stars wouldn't dip below the horizon in sync. They'd slide past each other at odd angles, casting jagged, shifting shadows. Science fiction often treats twin suns as a scenic backdrop, ignoring the gravitational havoc they wreak. In pitch black, the planet's constant daylight seems plausible until you realize a tidally locked world would have a blistering dayside and a frozen nightside, not the uniform wasteland shown on screen. Even Interstellar, praised for its scientific rigor, glossed over the radiation bombarding its binary orbiting planets. Real-life binary systems bombard their worlds with stellar winds from both stars, stripping atmospheres and triggering auroras that would light up the entire sky. But some fictional works get surprisingly close to the truth. The three-body problem novels depict a planet in a triple-star system, a scenario even more chaotic than binaries, where civilizations rise and fall based on unpredictable stellar orbits. It's a chillingly accurate portrayal of how celestial mechanics could shape a society's survival. Even Star Trek occasionally nods to real science. In one episode, a binary system's habitable zone is depicted as a fluctuating ribbon, mirroring astronomers' models of how these zones warp with stellar motion. The biggest misconception: stability. Movies often show binary planets as eternally sun-drenched, but reality is messier. Imagine a world where seasons last decades, where summer means both stars blazing overhead and winter is a dim, solitary glow. Forests might wither under double sunlight, only to regrow during cooler interludes. Intelligent life here wouldn't just track days, it'd forecast stellar alignments like we predict monsoons. Where sci-fi truly shines is in hinting at the cultural impact of twin suns. On Tatooine, the binary stars are woven into mythology and daily life, a detail that rings true. A real binary planet's art, religion, and even language would revolve around its skies. Calendars might count orbits, not years. Navigation could rely on stellar phases rather than magnetic poles. These are the nuances Hollywood often misses, not just the physics, but how profoundly two suns would redefine existence. The line between fiction and reality isn't just about accuracy, it's about imagination. Science gives us the equations, stories give them meaning, and while binary systems may not look like Tatooine, they're every bit as wondrous, challenging us to envision life not as we know it, but as the universe dares it to be. Kepler-47 isn't just another binary star system, it's a cosmic laboratory, a place where the universe tests the limits of what a planetary orbit can endure. Nestled roughly 3,000 light-years away in the constellation Cygnus, this system hosts two stars locked in a tight embrace, a primary star about the size and mass of our Sun, and a smaller, dimmer companion just one-third its size. Together, they orchestrate a delicate dance, completing an orbit around each other every 7.5 Earth days. But the real marvel, the planets that defy all odds to circle them. 3 worlds call this chaotic realm home, each enduring gravitational forces that would rip most planets apart. The innermost, Kepler-47b, races around both stars in just 49 days, a blistering orbit that leaves it scorched and likely stripped of any atmosphere. Then there's Kepler-47c, the crown jewel of the system, a gas giant straddling the outer edge of the habitable zone. With an orbit lasting 303 days, it's a world where liquid water could exist, if not for its puffy, Saturn-like composition. And the latest discovery, Kepler-47d, tucked between them, a Neptune-sized enigma with an orbit so precise it teeters on the edge of instability. What makes this system so extraordinary isn't just the planets, it's the way they persist. Binary stars should, in theory, shred protoplanetary disks before worlds can form. Yet here, planets coalesced in the chaos, their orbits stabilized by a rare gravitational sweet spot. Kepler-47 stars orbit so closely that, from the perspective of their planets, they're almost a single, flickering light source. This proximity creates a habitable zone that wobbles but never vanishes, a fluctuating band where temperatures balance precariously between ice and fire. The implications for life are tantalizing. While Kepler-47c itself is a gas giant, any moons it harbors could be prime real estate, hidden oases where tidal heating warms subsurface oceans beneath icy crusts. Imagine a moon like Europa, but bathed in the blended glow of two suns, its tides churned not just by a planet's pull, but by the star's competing gravity. Microbial life might thrive in these shadowed oceans, fed by hydrothermal vents and shielded from the system's erratic radiation by the gas giant's magnetic field. But the real lesson of Kepler-47 isn't just about habitability, it's about resilience. This system proves that planets can survive, even thrive, in environments we once thought hostile to stability. If life exists here, it wouldn't follow Earth's playbook. It might pulse with the rhythm of stellar eclipses, its biochemistry tuned to erratic energy inputs, its evolution shaped by necessity rather than consistency. The takeaway: binary systems aren't dead zones. They're crucibles, places where the universe experiments with extremes, forging worlds, and perhaps life, in ways we're only beginning to fathom. And if Kepler-47 teaches us anything, it's that life's chances aren't bound by our assumptions. They're written in the stars, sometimes in pairs. Red dwarfs are the quiet giants of the galaxy, small, dim, and astonishingly numerous, making up about 75% of all stars in the Milky Way. But when two of these faint embers orbit each other, the result isn't just double the longevity, it's a paradox of stability and chaos. Binary red dwarf systems are cosmic endurance artists, burning for trillions of years, far outstripping the 10-billion-year lifespan of stars like our Sun. Their combined glow might be feeble, barely casting shadows on any orbiting planets, but that faint light lingers for epochs, offering life an almost unimaginable timeline to emerge and evolve. Yet survival here demands weathering storms fiercer than anything Earth has ever known. Red dwarfs are infamous for their tantrums, sudden, violent flares that can double their brightness in minutes, bombarding nearby worlds with X-rays and ultraviolet radiation powerful enough to strip atmospheres. In a binary system, these outbursts can synchronize, with one star's eruption triggering its companion into a matching fury. Picture a planet caught in the crossfire. Just as it recovers from one flare, another strikes, leaving its surface scorched and its air thin. Proxima Centauri, the closest star to our Sun and part of a triple system, occasionally unleashes flares so intense they'd sterilize Earth like worlds within hours. Now imagine two of them taking turns, but life, if it exists here, wouldn't play by Earth's rules. Deep underground or beneath miles of ice, microbes could thrive in subterranean oceans shielded from the radiation chaos above. Tidal forces from the star's gravitational tug-of-war might keep these hidden seas liquid, just as Jupiter's pull warms Europa. Alternatively, organisms could evolve radical defenses, biofluorescent coatings to dissipate UV radiation, or cellular repair mechanisms that rebuild DNA faster than flares can damage it. Some might even harness the flares, treating each outburst as a burst of energy to be absorbed and stored, like desert plants waiting for rare rains. The real wildcard is the star's longevity. With trillions of years to experiment, evolution in a red dwarf binary could craft organisms far stranger than anything in our solar system. Intelligence, if it arises, might develop at a glacial pace. Cultures with millennia-long lifespans, recording history in layers of sediment rather than books, or civilizations that treat stellar flares as natural cycles to be weathered, not feared. For all their violence, these systems offer something precious: time. While single stars like our Sun flicker out after mere billions of years, binary red dwarfs could keep their planets warm until the galaxy itself grows old. Life here wouldn't be a fleeting spark, it'd be an ember burning slow and steady in the cosmic dark. Rogue planets, worlds torn from their orbits and cast into the interstellar void, are already cosmic nomads of the darkest order. But in binary star systems, where gravitational tugs are twice as violent, the ejection process becomes even more dramatic. Picture a planet caught in the crossfire between two stars, slingshotted so fiercely it escapes their grip entirely, left to wander the galaxy without a sun to call home. These aren't just barren ice cubes. Some could harbor secrets beneath their frozen surfaces, where the crushing pressure of stellar betrayal gives way to unexpected refuge. Take tidal heating, for example. A rogue planet might seem lifeless at first glance, its surface frozen solid in the absence of starlight, but deep below, the remnants of its traumatic birth could still be simmering. The same gravitational forces that flung it away might have stretched and squeezed its core during ejection, leaving behind enough internal heat to maintain subsurface oceans for billions of years. Enceladus, a moon of Saturn, shows us how this works. Its icy shell hides a global ocean warmed by Saturn's tidal pull. A rogue planet, once part of a binary system, could mimic this on a far grander scale, its oceans churned by residual geothermal energy long after the stars fade from view. Then there's the question of energy. Without sunlight, life here couldn't rely on photosynthesis. Instead, it might tap into chemosynthesis, drawing sustenance from hydrothermal vents or radioactive minerals in the planet's crust. On Earth, entire ecosystems thrive around deep sea vents, where bacteria convert sulfur and methane into energy, supporting towering tube worms and blind shrimp. A rogue planet's inhabitants could take this further: organisms with ultra-slow metabolisms, adapted to eke out existence in near-total darkness, their life cycles stretched across millennia. Imagine microbes that hibernate for eons between vent eruptions, or creatures with bioluminescent lures to navigate pitch-black waters, their faint glow the only light in an endless night. But the real twist: rogue planets from binary systems might not be alone. Some could retain moons yanked along during their violent ejection. These moons, heated by the planet's lingering tidal forces, might become oases in their own right: small, icy worlds with subsurface seas shielded from cosmic radiation by thick crusts of ice. A binary system's gravitational chaos could even fling out pairs of worlds, rogue planets locked in a lonely dance through the void, their mutual gravity generating enough heat to keep hidden oceans liquid. The most haunting possibility is time. While stars eventually die, rogue planets could drift virtually forever, their internal oceans persisting long after their parent binaries have burned out. Life here wouldn't just be resilient, it'd be timeless, evolving in slow motion under ice shelves that never melt and skies that never lighten. If we ever find such a world, its biosphere might hold clues to life's tenacity in the universe's harshest corners, proof that even in the dark, life finds a way. Timekeeping under twin suns would require rewriting the very concept of clocks and calendars. On Earth, our days and years are neatly defined by a single star's rhythm, a stable heartbeat of light and darkness. But in a binary system where dawn might arrive twice a day or vanish for weeks, civilizations would need to invent timekeeping as fluid as their skies. Imagine a world where noon doesn't exist because the suns are never both overhead at once, where seasons aren't cycles but unpredictable waves dictated by the star's gravitational waltz. One solution might be abandoning sun-based time entirely. Instead of tracking daylight, species could anchor their calendars to geological or biological cycles, tuning into the pulse of tidal forces or the flowering of resilient plants adapted to erratic light. On a moon orbiting a gas giant, the parent planet's regular transits could serve as a metronome, casting shadows at intervals more reliable than the star's capricious dance. Or consider civilizations that measure time through atomic vibrations, creating artificial seconds divorced from celestial chaos entirely. But other societies might embrace the complexity, weaving their concept of time into the star's intricate motions. Picture a calendar with nested layers: short days marked by the rise of the brighter star, longer months tracking the fainter sun's cycle, and great years spanning the full orbital resonance between both. Their astronomers could develop equations to predict eclipses centuries in advance, turning celestial mechanics into both science and spiritual practice. Religious festivals might align with rare moments when the suns rise in perfect unison, or when their combined light casts a singular shadow, events as sacred as solstices on Earth. The most radical approach: living without rigid timekeeping at all. Cultures might structure society around tasks rather than hours, working when energy is abundant and resting when radiation flares make the surface uninhabitable. Leap cycles could fracture into polyphasic patterns, with naps taken during stellar eclipses and activity peaks when both suns blaze. Clocks, if they exist at all, might display probabilities, a percentage chance of daylight returning rather than fixed numbers. What emerges is a profound truth: time isn't universal. It's a negotiation between life and its environment. For civilizations under twin suns, the very idea of measuring existence would become an act of defiance, a way to carve order from celestial anarchy. And if we ever encounter their artifacts, their clocks might not look like devices at all. They could be living membranes that pulse with tidal rhythms, or stone monuments aligned to capture fleeting moments of gravitational harmony. In such a world, timekeeping wouldn't just track moments, it would be a testament to survival. A civilization born under twin suns wouldn't just adapt to their light, it would weave them into the very fabric of meaning. Picture mythologies where creation begins not with one divine spark, but with a celestial argument between rival sun gods, their eternal dance shaping the rhythms of life and death. Art might abandon static forms altogether, favoring flowing sculptures that twist like binary star orbits or paintings that change hue under different stellar angles, capturing the sky's capricious moods. Every brushstroke, every chisel mark would echo the duality overhead, not as a choice but as the only reality the artists have ever known. Religion would likely orbit the stars' relationship, interpreting their motions as cosmic dialogue. Some cultures might revere the larger sun as a father figure and the smaller as a rebellious child, their eclipses symbolizing moments of reconciliation. Others could see them as lovers eternally chasing each other, their gravitational embrace a metaphor for devotion. Rituals might align with rare celestial events like syzygies where both suns perfectly overlap, transforming astronomical phenomena into sacred holidays. And what of eclipse seasons when one star blocks the other? These could be times of societal reckoning where communities fast or feast based on whether the dominant light is gentle orange or harsh blue-white. But not all interpretations would be peaceful. Societies living on worlds with erratic climates might personify their suns as capricious tricksters, their alignment dictating famine or fortune. Imagine temples where priests track stellar positions with obsidian mirrors, not to predict harvests as Earth's early astronomers did, but to appease volatile deities. Fear could inspire staggering architecture, underground cathedrals carved as refuges from flare storms, or towering obelisks that channel double sunlight into beams used for sacrificial rites. The stars' very unpredictability might birth fatalistic philosophies where free will is considered an illusion beneath the tyranny of celestial mechanics. Language itself would bend to the sky's rules. Color vocabularies could explode with terms distinguishing the blended gold-purple of simultaneous sunrise from the stark crimson of a lone star's dawn. Poets might compose in binary meter, mirroring the stars' orbital periods, while folktales warn of tide children, mythical beings born during gravitational extremes. Even mundane phrases would carry cosmic weight. A greeting like "May your shadows never cross" could be both blessing and survival advice, referring to the deadly heat of dual zeniths. The arts would face unique technical challenges. Theater performances might require adjustable lighting to mimic the stars' shifting brilliance, while music scales could incorporate harmonic ratios based on orbital resonance. Dance troupes might perfect movements that mirror celestial mechanics, spirals within spirals, a physical echo of their world's gravitational choreography. Yet the most profound cultural shift would be epistemological, how these civilizations understand knowledge itself. Earth sciences grew from observing predictable cycles, but binary cultures might prioritize probability over certainty, their mathematics favoring fluid models that account for celestial chaos. History books could be written in overlapping timelines, each sun's influence charted separately. Education might focus less on memorizing facts and more on interpreting patterns in noise, a skill vital for survival under erratic skies. Perhaps the ultimate cultural artifact would be their concept of home. To Earthlings, a single yellow sun means warmth and stability, but to beings raised under twin stars, a solo sun might feel lonely, even threatening, a broken system lacking the dynamic balance they've always known. Their nursery rhymes, their love songs, even their grief rituals would resonate with the understanding that existence is, at its core, a dance of opposing forces, and that beauty lies not in the stillness but in the orbit. Humanity has always looked to the stars with dreams of new homes, but none of our terraforming blueprints account for twin suns. Colonizing a binary star system wouldn't just require adapting to a new world, it would demand reinventing our very approach to survival. Picture the first settlers stepping onto a planet like Kepler 16b, where the horizon bends under the weight of two competing gravities, their first challenge. Redefining shelter, Earth's habitats rely on predictable day-night cycles, but under twin suns, buildings would need dynamic exteriors, perhaps metamaterials that adjust opacity as radiation levels spike, or rotating foundations to distribute heat evenly during eclipses. Cities might cluster around geothermal vents, using the planet's internal heat as a stable backup when stellar energy fluctuates. Agriculture presents an even thornier puzzle. Our crops evolved for a single sun spectrum, but binary systems bombard planets with mixed wavelengths. Greenhouses would need triple-layer glass to filter harmful UV from one star while amplifying infrared from the other, creating artificial Goldilocks zones for growth. Hydroponic towers could circulate nutrient-rich water in sync with tidal forces, mimicking Earth seasons through mechanical rhythm rather than celestial cycles. And forget about pollinators. Robotic drones might handle fertilization in environments where insects can't survive radiation swings. Energy infrastructure would undergo a revolution. Solar panels designed for a single star's output would fry under dual bombardment. Instead, colonies might deploy smart mirrors in orbit, reflecting and diffusing sunlight to avoid overload while storing excess energy in molten salt reservoirs. Fusion reactors could provide a steady baseline, their deuterium harvested from the planet's hydrogen-rich atmosphere, a necessity during the weeks-long eclipses when both stars vanish behind one another. The wild card is human biology. Even with technology shielding us, prolonged exposure to variable gravity and radiation could rewrite our physiology. Future colonists might undergo gene therapy to enhance DNA repair mechanisms or develop melanin variants that act as natural radiation shields. Sleep cycles would fracture without consistent darkness, leading to culture-wide adoption of polyphasic rest patterns synced to stellar motions. Over generations, settlers could evolve thicker skin, more efficient circulatory systems, or even altered eyesight to pass the kaleidoscopic skies. Yet the greatest adaptation wouldn't be physical, it'd be psychological. Living under twin suns means abandoning Earth's temporal certainties. Clocks based on planetary rotation become meaningless when days have no fixed length. Societies might measure time in stellar resonances, tracking the harmonic intervals between eclipses. Art and music could incorporate non-repeating fractal patterns, reflecting the chaotic beauty overhead. The very concept of home would expand to encompass duality, a cultural embrace of balancing extremes. Terraforming such worlds might be a pipe dream, but bioforming ourselves could be the key. Instead of forcing alien planets to fit human needs, we might engineer humanity to thrive in their chaos. Synthetic biology could let us photosynthesize during lean times, while cybernetic implants filter atmospheric toxins. The ultimate irony, by adapting to binary stars, we wouldn't just conquer new worlds, we'd become something new ourselves. Finding alien life in binary star systems isn't like scanning a single star and hoping for the best. It's more like tuning a radio between two overlapping stations, filtering out static to catch a clear signal. Astronomers approach these chaotic environments with a mix of ingenuity and specialized tools, recognizing that the very forces that make binary systems hostile could also make them hotspots for life. The hunt begins with targeting the right systems. Not all binaries are created equal. Some are too chaotic, their gravitational drama ripping apart any chance of stable planets. But others, like Kepler-47 or Alpha Centauri, offer just enough stability in the chaos, close enough for stars to share a habitable zone, but not so close they shred their planetary disks. The James Webb Space Telescope has become the crown jewel in this search. Its infrared capabilities pierce through the dust and glare of binary systems, revealing the subtle wobbles of orbiting planets and the chemical fingerprints of atmospheres. Unlike older telescopes that struggled with the overlapping light of twin stars, Webb's precision can distinguish between the two, teasing apart their individual influences on any worlds caught between them. But Webb isn't alone. Ground-based observatories like the Very Large Telescope in Chile use adaptive optics mirrors that warp in real time to cancel out atmospheric blur, to track the gravitational tug-of-war between binary stars and their planets. These observations reveal not just where planets are, but how they move, offering clues about their potential for life. Then there's the transit method, where astronomers watch for the faint dimming of starlight as a planet crosses in front of its sun. In binary systems, this gets complicated. Imagine trying to spot a moth flying between two flickering light bulbs. New algorithms now pass these chaotic light curves, identifying the telltale dips of planet transits even when they're drowned in stellar noise. NASA test mission, designed to hunt for exoplanets, has been retrained to prioritize binaries, its cameras scanning for those rare, rhythmic shadows that hint at a world threading the needle between two stars. But spotting a planet is just step one. The real prize lies in analyzing its atmosphere, a task that demands next-level spectroscopy. When a planet transits, starlight filters through its gases, leaving behind chemical barcodes. In binaries, these signals are jumbled, but tools like the upcoming Habitable Worlds Observatory aim to untangle them, hunting for biosignatures like oxygen or methane. The trick: timing observations during quiet periods when both stars are least active, minimizing flare interference. Perhaps the boldest strategy is listening rather than looking. SETI radio telescopes like the Allen Telescope Array now scan binary systems for artificial signals, focusing on frequencies that could pierce through the natural radio noise of twin stars. It's a long shot, but if a civilization evolved under two suns, its technology might be built to cut through the chaos, broadcasting in pulses or patterns tailored to stand out from the storm. The search for life in binary systems isn't just about having the right tools. It's about rethinking what habitability even means. These aren't just oddball environments, they're stress tests for life itself. And if we find something there, it won't just answer whether we're alone. It'll redefine what's possible. Binary star systems are cosmic paradoxes, places where the rules of habitability aren't just bent, they're rewritten. We've journeyed through worlds where day and night are fluid concepts, where gravity sculpts landscapes like wet clay, and where life, if it exists, dances to a rhythm unlike anything on Earth. These aren't just exotic backdrops for sci-fi fantasies, they're laboratories for the universe's most extreme experiments. From tidal heated moons to rogue planets adrift in perpetual night, the challenges are mind-bending, but so are the possibilities. Radiation, gravitational chaos, erratic climates, any one of these could spell doom, yet life might not just endure. It could thrive, evolving adaptations so radical they defy our imagination. Consider the resilience woven into these scenarios: organisms that photosynthesize across multiple light spectra, civilizations that build cities to flex with tectonic tides, ecosystems that pulse with the rhythm of eclipses. The very forces that seem hostile might be the crucible for life's most astonishing forms. And while Earth's quiet orbit around a single star feels like a sanctuary, it's also a limited perspective. The universe doesn't play favorites, it thrives on diversity. What if life isn't the exception but the rule, appearing wherever physics allows, even in the harshest corners? Now it's your turn. Do you think binary systems are cosmic death traps, or could they be bustling hubs of alien ingenuity? Maybe Earth's calm corner of space is the oddity, and the real action is happening under twin suns. Drop your theories in the comments. Are we alone, or is the galaxy teeming with life we've yet to recognize? And if you're hungry for more deep dives into the universe's wildest what-ifs, hit subscribe. The cosmos is vast, unpredictable, and far stranger than fiction. Let's keep exploring it together.